good moment to start this April session of the young seminar series of the Italian Physical Society, Statistical Physics Society. And today we have two speakers, Giuseppe Fava and Rosalba Pacelli. With Giuseppe Fava, Giuseppe is currently a postdoc at University of Suzhou and Sorbonne University in Paris, and he got his PhD in physics at the University of Insubria, Como, Italy, with a thesis on out of equilibrium physics flocking active matter systems. So his expertise is primarily in out of equilibrium physics and in particular on flocking active matters. And in fact, he will present today a talk on boundary symmetry breaking in polar active matter. So please, Giuseppe, the floor is yours.
Okay, thank you very much for the kind introduction. Just give me 1 second to share my screen. Okay, can you see?
Yes, yes.
Okay, so I'll start. So once again, okay, thank you to the organizers for this rich opportunity to, in particular, to share my work. So today we'll present this work, Boundary Symmetry Breaking in Polar Active Matter, which is based on two papers that I've done together with my supervisor, Francesco Ginelli, and with Professor Gambassi and a former postdoc, Leonardo Lenzini. So first of all, what is active matter and what are active matter systems? So active matter systems are a system that can extract and dissipate energy and use such energy in order to self-propel and move in their environment. And this is mainly the reason why we believe and these systems are out of equilibrium. Now, examples of active matter systems range from starling flocks that have been studied from the group in Rome to down to the scale of microtubule bundles. And recently, active matter systems have also been studied synthetically. So there are synthetic realization of such systems. So for example, the last picture is about colloids suspended in water that are able to basically mimic the behavior of 2D liquid crystals, living crystals, sorry. Now, whenever we speak about active matter, this is fairly generic, and in this presentation, I will focus in flocking active matter. Now, flocking active matter systems are a system that spontaneously break a continuous rotational symmetry to achieve collective motion. And as I said before, this is the case, for example, in starling flocks, which of course flock. This behavior, so flocking, has also been observed down to the scale of epithelial tissues. And in particular, it has been what has been capturing the eye of the statistical physics community is the fact that in the ordered phase, in the polar ordered phase, these systems display long-range order. And in particular, this is exemplified by the fact that in starling flocks, the correlation length of, for example, the orientation spans the flock size. And for the case of epithelial tissues, that the structure factor, for example, the density structure factor, is divergent in the low Q limit. And of course, whenever a physicist encounters these problems, he tries to model them. And probably
Giuseppe, sorry, yeah. There is a banner in your in your slide. If you can hide the banner, that's better. Okay.
Okay,
thank you.
So and whenever a physicist encounters these problems, what he tries to do is to model them. And perhaps the simplest microscopic model that describes a transition to collective motion is the what is known as the Wicksec model. And its 2D dynamics is fairly simple. and relies on this discrete time update, where positions and orientations are updated as I have written here. And basically particles self-propel and then align with some ferromagnetic rule, as in, for example, in the XY model. Obviously, this alignment is contrasted by a white noise term, which makes alignment imperfect. And for sufficiently low values of the noise, this system describes a transition to a polar liquid phase, which is characterized by long-range correlations between the orientations of the particles in our systems, and in particular, all of the system is flocking. Moreover, this model is also characterized by particle number conservation, which means that no particles die or get created in the process, and which one also last, let's say, symmetry or absence of symmetry. There is no Galilean invariance in such model because these particles are thought to be moving on a dissipative substrate. And this means that there is a frame, a reference frame, which is the frame of the substrate, which is preferential. One can finally work out the full microscopic, the full phase diagram of the system, and sees that basically it displays three different phases: a disordered gas phase, polar bands for intermediate values of the noise, which is this red region over here, where you observe polar traveling bands in a disordered gas, and as I said, a polar liquid phase, which is the interest of this talk. On, let's say, a more analytical description, such flux can be also described in terms of a hydrodynamic description, which relies on the slow fields, which means those quantities which are able to describe our dynamics for fairly long times. And in particular, these are associated always to conservation laws, and perhaps also to broken symmetries, or in general to symmetries. So in this case, one can write down also a hydrodynamic description for flocking, which relies on an equation for the density, which expresses density conservation, an equation for the velocity, which is basically an Navier-Stokes equation, where the absence of Galilean invariance admits also several other nonlinearities in the velocity. Furthermore, there is a Ginzburg-Landau term which instead promotes non-zero velocity in the polar ordered phase. And the D terms, so the diffusion constants, reflect instead the tendency of localized fluctuations to spread out due to alignment interactions. And finally, F is a random noise, a random force representing a Gaussian noise. Now, one can study this theory at the linearized level by simply expanding around a reference density ρ0 and a reference velocity p0. And what one finds by doing the proper calculation is that the density and velocity structure factor, which is basically the Fourier transform of the correlation function, scale as q to the -2, which indicates that in d equals 2, at the linearized level, there is long-range order cannot be predicted. So what has been implied during the years is an approach which can also take into account the nonlinearities, which is the dynamical renormalization group. And basically this consists in averaging the equations of motion, the nonlinear equation of motions, over a small shell, and then rescaling the coefficients in the nonlinear equation of motion, so to get a new set of equations with rescaled parameters. And the idea is to find a nonlinear fixed point where all our parameters do not get renormalized anymore. And this has been carried out during the year, and it's now clear that at the nonlinear fixed point, and taking into account nonlinearities, one finds that both the velocity and the density structure factor scale as q to the minus z, which is correctly found to be smaller than 2, which obviously supports the idea that one has long-range order also in 2 dimensions. And here for reference, I have written both the numerical estimates and analytical predictions of these exponents in the equals to for the anisotropy, dynamical, and roughness, just to give a general idea. Now, whenever active matter interacts with boundaries, we get some fairly counterintuitive results, given to the fact that they defy, let's say, our intuition of equilibrium physics. Probably the simplest way to see this is by noting the spontaneous compression of an asymmetric piston. So if you prepare a system with homogeneous density and place an asymmetric piston, let's say, in between, this is made of basically 2 different materials on 2 sides. One is soft and one is stiff. And if you prepare it with, let's say, circular active particles, what you see is what you observe here on the left-hand side. So basically, you get what you would expect from equilibrium, and the piston stays, fluctuates around the middle. Instead, if you take elliptical active particles, the system compresses in one direction. In particular, it compresses the side with the stiff wall. And this is kind of counterintuitive because it's not observed in equilibrium. Furthermore, of course, in experimental system, confinement has been used, and it's a clever way to control systems that flock, because obviously you don't have a huge laboratory, so you want to control and to localize your flock. And in particular, for example, this ring geometry has been proposed as a way to obtain and to control a flock. And also, I would like to recall that confinement pins the direction of flocking, which is also then fairly useful in terms of data analysis. Now, moving actually to my research, so what I have done together with Francesco and Professor Gambassi is so we wanted to understand what was the effect of confinement on a flock. And so to do so, we prepared, we have done several simulations of a flocking system confined in the transversal direction, implying reflecting boundary conditions in this direction, and instead periodic boundary conditions in the longitudinal one. And whenever particles try to cross the wall, they are reflected away, as shown here on the right. And basically, they're prevented to go outside, and torque is applied to the boundaries, which means that whenever they cross, then their direction after collision will be either totally reflected for this beta parameter equal to 1, or partially reflected whenever beta is smaller than 1. And of course, one expects that confinement breaks transversal invariance, and this is clear from these 3 profiles that I show here, which are the density deviations, the polar order, and velocity fluctuations. And indeed, one expects depression of fluctuations at the boundaries, which then induces an accumulation of particles at the wall. And this is nothing really new, because accumulation at boundaries has been observed in active matter systems. But what is fairly new is that this accumulation at boundaries, if one carries out the proper finite size scaling analysis, is actually extensive. So what we obtain in our case is that the deviations of density happen in a region which is a finite fraction of the system size when taking the system size that goes to infinity. And we can do so by simply calculating this d0, which is a zero crossing. So basically, we find whenever these density deviation cross 0, and we register this number. And this, as you can see, goes to a plateau when rescaled by the system size in the transversal direction. So this means that there's a finite fraction of the system where the excess density is positive. And here it's shown for several different transversal wall separations, and for this parameter, reflection parameter beta, taken to be equal to 1. So we obtain extensive boundary layers, but in the thermodynamic limit, we actually recover the bulk. So it means that if we take the total density deviations, so the total magnitude of this density deviations goes to 0 as 1 over the square root of r. Now, the extensivity of this, these boundary layers led us to think that we could also capture the density profiles and velocity profiles through a hydrodynamic approach. And this is what is presented here. So in this case, I'm presenting results from a simplified version of the 202 equation, in which we have dropped some nonlinearities from the velocity equation, which is nevertheless still accounts for most of the physics of flocking. And we have added also a positional diffusion, which is nevertheless present whenever performing DRG calculations. So it gets generated by the flow. And by proceeding by a spin wave approximation, so keeping basically expanding rho naught around, so density around a reference density rho naught and velocity around a reference velocity p naught, and using, of course, all of the symmetries of our problem, so Casimir symmetry and employing stationarity, we obtain an equation for the density deviations, which is written here below, and it's fairly easy. Now, if we forget of the right-hand side, on the left-hand side, we simply have an ordinary differential equation, partial differential equation, which has been found previously in the context of confined scalar active matter. And in particular, this leads to local boundary layers, which means that, let's say, the excess density is in an intensive region close to the wall. So in the thermodynamic limit, this region will, let's say that the relative size of this region will go to 0. Instead, in this case, we keep this term on the right-hand side, which takes into account bulk colorations of our flock and evaluated through the velocity structure factor. This is what we do here. So one can simply perform the calculations in Fourier space because it's easier, especially for the velocity fluctuations. And one can obtain the velocity fluctuations profile, basically integrating the velocity structure factor modified by the fact that we have a system which is confined, and the full expression is reported in this paper here. I won't show it over here because it's a bit it's relatively easy, but it doesn't really highlight much and help in understanding. So basically, if we use this modified density structure factor by the presence of confinement, and with proper boundary conditions, we can obtain an equation for the velocity fluctuations, which is expressed as a sum. And performing numerically this sum, we obtain the actual velocity fluctuation profile, which is here reported in blue. And instead in red is the data obtained from microscopic simulations. And as you can see, the agreement is pretty good. Now, once we have the velocity fluctuations profile and these modes, we can then feed them back into the equation for the density, this one, and write down an equation for the density profile. And this relies basically on two coefficients, which are this C and gamma, which are left as free parameters. And as we did for the density, for the velocity fluctuations, we can perform numerically this sum, leaving C and gamma as free parameters. And what we obtain is shown here on the left-hand side, which is a very good agreement with the density deviation profile coming from microscopic simulation. So black is data and red is our theoretical prediction. And in particular, we observed that this fit basically does not really rely on the exact value of gamma, indicating that the relevance of higher order derivatives is fairly small. So gamma controls higher order derivatives, as you can see from this equation over here. Furthermore, we also recover the correct scaling. So we find that by performing this, numerically summing this equation, we obtain that the density profiles are extensive. So there's a positive region of excess density, which is a finite fraction of the system. So this D0 scales with R, and also that the density deviations go to 0 as 1 over the square root of R. And finally, we also then measured the mechanical pressure exerted on the boundaries, because of course this accumulation generates a pressure which depends on wall separation. Now, of course, as I have shown before, mechanical pressure in active matter depends on boundary particles interaction. I have shown the case of perfectly so elliptical versus circular particles, and in particular, it depends on how momentum is dissipating in the surrounding media and also with the boundaries. Now, these details are left unspecified in the Dixit model. And so we took two different definitions of the pressure and then verified that they were consistent. So one possible definition of this boundary pressure is simply given by the average number of collisions per unit length, which is fairly easy to measure in numerical simulation, in microscopic simulations, and has a microscopic analog, which is basically minus the force density exerted by the particles on the wall, which is this expression here. And for a sharp potential, which mimics the effect of boundaries, this name gives basically the pressure at the boundaries. And finally, a second expression for the boundary pressure relies instead on the momentum exchange at the boundaries. Now, as you can see from the theoretical perspective, we can calculate this boundary pressure as the density deviations at the boundary, which can also be calculated analytically from the expression that I've shown you before. And obviously, this is one single point, so this can also be carried out analytically, and we find this expression, which is made basically of two different contributions. A first one, which is PB of infinity, so which is correctly found to be positive and represents the boundary pressure exerted by a semi-infinite system. And then instead the finite size correction, which depends on wall separation through 2 chi, which is the roughness exponent. Chi is the roughness exponent of the theory, and is correctly found to be negative. And from the microscopic point of view, we find a very good agreement of the boundary pressure with the theoretical expectations. In particular, the boundary pressure fits very well with this 3-parameter fit, which takes into account a boundary pressure of the semi-infinite system, and then some finite size correction depending on an exponent alpha. Now, this exponent alpha is found to be dependent on the fitting region, which typically suggests a crossover from some, let's say, small value to larger values, or in general, the crossing of some scales where certain nonlinearities can become relevant. So to further analyze why we had this let's say this growth of the exponent, of the Casimir exponent, we actually measured the derivative of this curve, and we found that basically we have a crossover from a small value of alpha, which is around 0.4, to a larger value, which is roughly 0.6. And finally, we have also measured this different pressure based on momentum exchange, so taking into account also the transversal direction of particles heading towards the wall. And what we have found is that there is no significant difference with the case of number of collisions, as you can see from the fact that the ratio between these two pressures is roughly constant. And also this result holds regardless the boundary interaction, so regardless of how the particles exit the wall, but nevertheless, we need this, this parameter beta to be greater than 0. So we need particles to go away from the wall whenever they try to cross it. And finally, all of these results were shown to be hold generically in the polar liquid phase. And with that, I would like to conclude and thank you for your attention.
Thank you very much. Are there comments? We have some time for 1 or 2 questions. Is there any question or comment? I have one question concerning the geometry. Is that correct that the geometry is just, let's say, a linear geometry between 2 parallel boundaries in the system?
Yeah.
Yeah. And is this I mean, is this affecting the description, you know? Because I believe,
Yeah, no, of course. I mean, the point is that, so this was one concern we had at the beginning, because of course, whenever you fix the direction of motion, you're not actually explicitly, you're explicitly breaking the symmetry. And so this actually, I didn't have time today because of the restriction in time, but you can show that this induces a mass that can be detected. And in particular, it can be detected in the longitudinal direction. So if you calculate the structure factor in the longitudinal direction, you can basically know how narrow of your geometry, how narrow your geometry is.
But can you, I mean, you did from time to time, let's say, a parallel analogy with the hydrodynamics modeling, right?
Yeah.
Could you also imagine that you have a kind of threshold beyond whom you would have a kind of chaotic or just very complex behavior in the system?
Might be. You mean a threshold in what? In length scales or?
It could be in landscape or in density, I believe.
Yeah, it can be. I mean, in terms of perturbations, these let's say flat repelling boundaries are fairly a gentle perturbation. So people have studied the disordered boundaries, which instead create more complicated, complex dynamics. In this case, I have to say, to my knowledge, I wouldn't expect chaotic dynamics, but it's something we haven't looked at. So,
okay. Any other comment or question? So if not, thank you again for your presentation, Giuseppe.